So that's the final temperature of the water, which is 90 degrees centigrade. How hot was the iron when it was first removed from the flame? Specific heat of iron is 0.473. Final temperature of the iron, initial temperature of the iron, we don't know. Right? That's what it's asking for right here, people, right? And the final temperature of the iron has to be what? 90 degrees, right? Because we go through that same thing, well, everything's together at thermal equilibrium at the end of the experiment, okay? So that's going to be 90 degrees on both of those. So basically, our equation here is already set up, right, from the last time. We're just going to have to plug and chug. And it'll actually be easier than last time because the algebra won't be as stepwise. All right, not that this was a major stepwise thing. Okie dokie. Mass of the iron, 500. Negative sign, 0.473. 90 minus, don't know, equals 400. 4.184. 90 minus 10. All right, now I'm going to prefer to go ahead and do the left-hand side, the right-hand side first because there's no variables. 90 minus 10 is 80 times 4.184 times 400. Here's what we've got. 133,888 joules. Now, negative 500 times 0.473, all right, is going to be negative 236.5 times 90. So that's going to be negative 21,285. Do you see that? I multiplied these three numbers together and distributed in on top of that 90 to get that number. Now I'm going to take that number, which is negative, and multiply it by that, so that's going to be a positive 236.5. All right, X. So now let's see here. Let's go ahead and keep the X on the left, and let's take 133,888 plus 21285. All right. 155173. 236.5x. Okay, so now x is going to equal 656.1. Again, what is x? Well, x is over here. That's the initial temperature of the iron. All right, 656 degrees centigrade was how hot it was when it hit that. All right. So again, maybe this could be a way to take the temperature of a metal without sticking a thermometer directly to the metal, right? Because naturally, a normal thermometer, right, one that you would find in a normal freshman chemistry test lab, and that would go like from negative 10 to 110, something like that. All right. So this would be a way you could take it with a normal thermometer in water. I mean, they certainly make thermometers that go up to 400 or 500 degrees centigrade. All right, but they're very expensive and long and everything else, yeah.
Question. Yesterday in the experiment,
Mm-hmm.
when you dropped the iron in the water, why did you pick the highest temperature? Like you didn't just wait until it settled, like you normally take the highest temperature of the water.
Oh, okay. That would be when you're measuring this temperature here, the final temperature. All right. And what we did yesterday in lab is we started out here, okay, basically if we were on an Excel spreadsheet, okay, if we were on an Excel spreadsheet, and this was time, and this right here was temperature, all right, we would start putting little dots periodically. Now, what would be the point of those little dots? To see where the stabilization is. Because, I mean, after all, if you take cold water out of the faucet, it's going to take a few minutes to get to room temperature, right? It's a little bit cooler than room temperature in most cases. And then whenever you do your metal addition, what's going to happen is that temperature is going to spike up, stable out, and then of course if you let it set all night or all day, it would come back to room temperature again, right? So whenever we try to find the temperature here, okay, we got little dots along this line over time. Maybe this is 0 minutes and maybe this is 2 hours. Who knows? Okay. So as you're measuring this, you're interested in whatever that peak was, the highest point for what's called a temperature maximum. All right. And then after that, what's going to happen is your ambient temperature, all right, what's your room temperature? We'll just start bringing it back down. So that's why you take the highest one. All right. What else we got? 40? Homogenized whole milk contains 4% butter fat by volume. How many milliliters of fat are there in a glass? Is that the one you want? Okay. You guys like buttermilk? You ever tried it? Yeah, you don't like it? Does anybody like buttermilk? One person? I like buttermilk. You don't know? It's normally considered a country thing, except for cooking. All right, but whatever. Here's what we got. It contains 4% butter fat, so 4% by volume. Okay. How many milliliters of fat are there in a glass? So 250 milliliters of a glass. How many grams of butter fat are there? So first off, it wants to know how many milliliters. That's part A. And part B wants to know how many grams of fat are there. Okay. And the density of buttermilk is 0.8 grams per milliliter, or the density of butter fat. Okay. So this is a byproduct of churning and making butter. That's why they call it buttermilk. And it tastes sour. You see there's bacteria and stuff in it. And it's basically, quote unquote, spoiled milk, kind of. All right. It's not spoiled milk, but kind of. All right. So here's what we've got here. If it's 4% by volume, so that means 250 milliliters times what? 0.04. That's 4% of that, right? So in every glass, I moved the decimal place 2 places to the left. 250 times 0.04, that's going to be 10 milliliters of butter fat per glass. All right, 10 milliliters of butter fat per glass. And if we look for the grams, it says how many grams will there be? Well, take a look at it. 0.8 grams per milliliter. So that's going to be 10 times 0.8. Why did I do that? I don't know. I'm getting tired. Is 8 grams of butter fat. Okay. So it's going to be 10 milliliters of butter fat or 8 grams. You see, like whenever you